if a given fatty acid has a double bond, then it is referred to as unsaturated fatty acid, and if it lacks a double bond, then it is a saturated fatty acid. And we talked about the different functions, okay, of consuming unsaturated fatty acids, the mono and the puffers, and then the disadvantages of consuming the saturated acids, where we saw that the unsaturated ones form kinks, like how you see, but for these ones they don't form kinks, so they can easily clog. Okay, they can easily clog. And examples of fatty acids and their occurrence: you have butyric acid. This one is just C3 and then COOH. You know, beauty means four, so it has four, and it is saturated, and you find it in butterfat. Then we have alpha linoleic acid, or you can call it omega 3. It is C17, and then COO. It is unsaturated, and you find it in most seeds, the G-nuts. But if you are feeding on G-nuts, then you are so good. This omega 3 and omega 6, these omega 3 and omega 6 fatty acids, they do improve on the attention span, okay, and processing capacity of an individual. So if you grew up feeding on G-nuts, feeding on most seeds, then you are good, you are kawa. Okay? Then we have oleic acid, which is C17, same, and it is unsaturated. It is found in all fats. Then palmitic acid, animal oils and vegetable oils, and it is saturated. Arachidic, and so on. There are very many. So you can have a look. These are saturated. You can see how they appear. Okay? And then these are unsaturated. They form kinks. Okay? And this is alpha linoleic. It has three double bonds. And this is gamma linoleic. And so you can have a look and appreciate the importance of this double bond. So at that point of saturation, you cannot clog. Okay? But for these ones, they can easily clog together. Okay? And form issues, challenges, like how we discussed in our previous lesson. So nomenclature of fats, let's talk about it briefly. So let's talk about nomenclature of these fatty acids, like said. And they are named, they are the same, they are organic compounds. Okay? Whereby they are organic compounds. For saturated ones, you just get the parent hydrocarbon chain and then you add the word oic. Remember, they are carboxylic acids. And with carboxylic acids, that's how we name carboxylic acid. For example, you remember when it's this CH3COOH. You get the parent chain, which is eth, and that is ethane, and then you add the word oic. So it is the same thing. Okay? But however, the parent chain here is kind of complicated because they do have very many carbon atoms. Okay, and for example, if it is carbon 18, then 18 is known as octadeca. So C18 is octadecane, but we remove E and add oic acid. So this is octadecanoic acid. Now that is the IUPAC, but the technical names, then those are the ones we've been saying: linoleic, alpha linoleic. However, for the other one, for the linoleic, for them they are unsaturated. But for this one, it is just saturated. Then for unsaturated ones, you have to indicate the position of the double bond. Okay? So if it has a double bond, then we add, instead of oic, then we add enoic. Okay? So for C18, then it becomes octadecanoic. Okay? Sorry. Sorry for that. So for carbon 18, it is the same nomenclature. If it's a double bond, remember double bonds are alkenes. So instead of alkanes N, then we add En and then OIC. So that is octadecanoic. Okay? Octadecanoic. Then with two double bonds, then we add dienoic. Dienoic. For example, if it is still our C18, the IUPAC name then becomes octadecadienoic. Okay? Octadecadienoic. With three double bonds, 3 is tri, then we add trienoic, and so it becomes octadecatrienoic. Okay? Yes. However, now this is not part of the syllabus. Let me say that. Somebody is knocking. Let me check on them. So basically, that's how we name these organic compounds. Alternatively, if you want to write them with ease, then you can also simplify it in this format. Or we can have alternative ways of writing these organic compounds, whereby you just write this represents a hydrocarbon chain, whereby this is the point of saturation. Okay? Now, you write 18, and the 18 shows the number of carbon atoms. Okay? And then you write 1. This 1 shows the number of double bonds. And then you write this, the triangle, and then you put the 9. The 9 shows the position of the double bond. So if you find it somewhere in a given textbook, they write 18, and then they put dots, and they write 2, and then another dot, and then they do this 6, 3 or 3, 6. So this shows that your fatty acid has 18 carbon atoms, and with 2 double bonds, and the double bonds are on carbon number 3 and carbon number 6. I think the 3 should come before 6. Okay? Yes.
What about C's?
Now the C's, this is isomerism. We have the trans and the C's. So this is shows the the structure, the isomer that you are dealing with. Okay, how these atoms are arranged across the double bond. Okay, it's what gives the Cs or the trans isomer. Whereby if the H is on the same side and the other groups also on the same side, and that one becomes the Cis isomer. But if one OH is here and then another one is here, if one H is here and another H is here, and then this group continues from here, and that one becomes the trans isomer. So basically that's how it is, just isomerism, what we studied in organic chemistry. But still, all that, no one is going to ask you that. Okay? Yes. And like I told you, I've ever told you this. This carbon atom here, okay? This one, this is a CH3. So this carbon atom is what is called the omega carbon. Okay? Or it is something of this kind. So this is the omega carbon. And then this carbon, this one, the COO, it is the alpha carbon. Okay? This is the alpha carbon. Are we together? So, if you want to name, if you don't want to give the IUPAC name, you can just give the position of the double bond in respect to this omega carbon. Okay? For instance, you may have the omega 3, the omega 6, the omega and stuff like that. It means that the double bond, if it is now like this one, the double bond is on carbon number 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is the omega 9, the omega 9 fatty acid. Why? Because the double bond is on carbon number 9 with respect to the omega carbon. So the omega 3, the double bond, okay, is on carbon number 3, okay, with respect to the omega carbon. This is going to be 1, this is going to be 2, and this is going to be 3. Then with omega 6, the double bond is on carbon number 6 with respect to the omega carbon. Now that one opposes the IUPAC, because the IUPAC, when we are counting carbon 1, 2, 3, 4, we consider the functional group, and this one therefore becomes carbon 1. But if you say omega 3 fatty acid, it means that the double bond, or the very first double bond, is on carbon number 3 with respect to the omega carbon. Okay? So we have been one of the properties. Yes?
I think I can try.
You can try to answer this, eh? Of course, this is your question. No, this is your question. Relax. You're going to answer it, of course, not me. Okay? You're going to answer it. So, one of the properties of the lipids is that they are insoluble in water, and it is obvious case. It's OVK. It's obvious case. Get your blue band, get your margarine, get your cooking oil, for instance. Cooking oil, and you shake it with water. It will remain insoluble. It won't dissolve in the water. Okay? So that is obvious case. From your basic understanding and from what we have just covered and from what we covered in both chemistry, organic chemistry, not physical, inorganic bonding, and when we basically from your basic understanding, how which explanation can you give for the insolubility of the lipids? Uh-huh. Okay.
It's
Okay, go ahead.
it's like the lipids are hydrophobic.
Uh-huh.
Is it? So they cannot dissolve in water like what should I say?
Anything.
They are hydrophobic and however
Mm.
water molecules
Mm.
are much greater, like let me say, they are repulsive to the lipids.
They are repulsive to the lipids.
So the lipids cannot dissolve into the water due to the repulsion.
Mm.
That's what I can say.
Okay. Okay, yeah. That's some brilliant idea. Some brilliant work. Okay? Mm-hmm. Anyone else? Anybody else to give it a shot? Because I have to listen to all your ideas. Okay? So, who is next?
Think me
Okay.
might think that lipids cannot dissolve in water
Mm.
simply because water is a proton acceptor.
Okay.
Also,
Okay.
but the lipids don't have anything to provide to the anything to provide any proton to provide what the lipids are made up. The water is a proton acceptor, accepting the hydrogen protons
Mm. Yeah.
onto it to form the H3. Oh,
Mm.
don't recall the name.
It is.
But the lipids
Mm.
don't have that proton that they can give to water to form
Mm.
the ions.
Mm.
That's how I can narrow it down.
Okay. Okay.
Teacher,
Yes.
teacher, do the lipids have a double carbon bond between them?
Yeah, it depends on the fatty acid.
Okay, to add on,
Yes.
like let me say, all fats and oils, they are non-polar substances, not so.
They are non-polar substance. Yeah, that is true.
And to borrow some chemistry yesterday, you say that polar solvents dissolve in polar, which is polar something. Then, like only polar solids dissolve in polar solvents.
Okay, that's good.
So these fats being non-polar, they cannot dissolve in the water because it's a polar solvent. Because
Okay.
of its double bond and the hydrogen carbons.
Okay. Okay. Anyone else?
I think the fatty acids they have got tails,
They have got tails.
and most of the time tails are hydrophobic or water repelling,
Hmm.
and I think it is the only reason as why the lipids don't dissolve in water.
Okay. So because they have got tails, and the tails keep repairing. So why do they repair? Yeah, basically this, you guys, you have nailed it all. Okay? If I combine your ideas, I can get, actually, I'll get the correct answer out of all your ideas. Okay? And the answer is simple. Anita, you were correct. That second submission, it was really good. That lipids are non-polar, they are hydrophobic, and you borrowed even microchemistry. That polar molecules dissolve polar solvents. Polar solvents dissolve polar molecules, and non-polar solvents dissolve non-polar molecules. Like dissolve like, okay, and unlike dissolve unlike. So the unlike molecules cannot. Anyway, in simple terms, the our hydrocarbon chain, it is a long chain of hydrocarbons. You can have a look. It is just this. It's just a long chain of hydrocarbons. And then with this long chain, you just have the COOH. And even as if that's not enough, you take away this, okay? And then you add a glycol, O, and then O, okay? And the rest are hydrogens. So, the Capora group is just small, too small. Actually, the oxygen that remains here, the other oxygen that remains here, and also the other oxygen that remains on that third hydrocarbon chain, it is what is kinda polar. But even if the polarity is too small, okay? And so because of this long tail of hydrocarbons, okay, which is non-polar, okay, and it's hydrophobic, then there is no way how the lipid or the fat is going to associate with water molecules for it to dissolve, okay? And therefore, the overall lipid is going to be insoluble in water. That was really good discussion. It was good. So the hydrocarbon chain may be very long. Obviously, it's long, forming long tails which extend from the glycerol molecule. These tails are non-polar and hence they are hydrophobic, which makes the lipid insoluble. Okay? Yes. So due to high carbon hydrogen chain, okay, relative to this polar group, this one, then the overall lipid that is formed is going to be insoluble in the water. Okay? Yes. Thanks for thinking. You thought well. It was kinda good, okay? Not just kinda, but it was really good. So if you understand that, then you should think about why formation of phospholipids. Anyway, we shall reach there. So in cell biology, we talked about a cell membrane, and we talked about the phospholipids. Okay? Yes. Where we said that a membrane is just an assemblage of very many lipids, and a protein molecule or protein molecules. So now you should be wondering, why not fats? Why not lipids, but rather phospholipids? Why not lipids, but rather phospholipids? And even before that, what is a phospholipid? So a phospholipid, it's a lipid derivative whereby one of the fatty acids of the lipid is replaced by phosphoric acid by condensation. Okay? By condensation. And a phosphodiester bond is formed. Okay? And it is that phosphodiester bond that is going to maintain that phospholipid molecule intact the way it is. Okay? So it is a major constituent of cell membrane in both prokaryotes, archaea, and eukaryotic cells. Majorly, all cells, okay, have what we call the phospholipids. So phospholipids, they are similar to fats, but they have two fatty acids, like we said. They just have two fatty acids, okay? Whereby the third, remember on the glycerol, which is, and we are going to see how the structure is formed, okay? The glycerol, which is this OH, okay? This is your glycerol OH. So it is going to use the two OH groups, okay, to bond with a 3 fatty acid. And then the third, okay, instead of bonding with a fatty acid, it will bond with phosphoric acid. This is phosphoric acid. And when name first, it is H3O4. Okay, that's phosphoric acid. Structure, we can draw this. You have O here, and then the rest are OHs. So this is OH, OH. So think about, in your mind you should be thinking, why a fatty acid? Why? Why phosphoric acid? Why? What is that unique feature does this phosphoric acid have that you are basing on, okay, to replace this fatty acid with a phosphoric acid? Okay, so the third hydroxyl group of a glycerol is joined to a phosphate group which has a negative electrical charge in a cell. I think we have a let's think. Do we have it? No, we have an illustration. So basically that's our phospholipids. Okay? And let's see, how are phospholipids different from a lipid? So if this is our lipid, you can see this is our space filling model of a lipid. This is going to be our glycerol, okay? And then these ones, they are the 3 fatty acids, okay, that are joined to the glycerol. And this is a lipid. But now for phospholipids, okay, you see, so one of the fatty acids, I don't know which one, whether this one, but one of them, obviously either on carbon 1 or carbon 3, one of them is going to be replaced by a phosphoric acid, okay? And phosphoric acid, like I said, it is H3PO, okay, whereby one of the OH, okay, one of the OH, so this is H3 and then H, so one of the OH bonds, okay, is going to condense with the OH on the glycol to form a phosphodiester bond, okay, which is going to hold this phosphoric acid to form a phospholipid. Not so? Yes. So you can have a look. You can have a look whereby this is our hydrocarbon chain, okay, and this is our glycerol. Now this is the carbon on the phosphoric acid. Then this is our glycerol. You can have a look. Let me change a pen. To which one? To red. So this is our glycerol, okay, and then this is our phospholipid for phosphoric acid, or our phosphate group. So in some molecules you might add there another group just to increase on the bulk in some phospholipids, okay, but these molecules, okay, they are important, of course, you can't add, but they are minor as far as phospholipids are concerned. So basically this is our phospholipid, okay, our phospholipid. So in case you have a query, it's okay, you can drop it in the chat box, or you can unmute and ask, okay. So again,
Teacher,
yes,
teacher,
yes, you
previous group, previous slide.
it's there.
No.
Mm-hmm.
What was the topmost functional group?
This one,
There is that functional group above the phosphoric head.
these are just, let me call them adhesive groups. This is just a group that is
Yes,
bound, okay.
just
It is it is just bound.
pardon.
I hope you can now hear me. Okay, this is just a group that is bound onto the phosphoric acid group, or the phosphate group, just to increase on the adhesive. Okay, but it doesn't have any big deal,
Mm.
okay.
You
Yes.
have which have had nothing.
However, it's not that it doesn't have any use, that's why it is there. But like I told you, no one is going to ask you about such a group, okay, according to your syllabus, okay. Yes. So let's think together again. So we have seen,
Excuse me, sir.
yes.
When we finished answering the other question, network checked me and I didn't hear the explanation for phospholipids.
Oh, so you want me to go back? Yes, I hope the explanation is now okay. So can we think through this? Can we find ways of answering this? So, like we said, you guys, your answers were correct, apart from, yeah, some few which require some modification. So you know that the lipid as a lipid is hydrophobic. It is relatively insoluble in water, hydrophobic. So now, if you add a phosphate group, remember phosphate group is like this. This is P and this is O, and the rest are OH. OH. And then OH. So you would use one OH to condense with the glycerol, and then you remain with this OH, you remain with this OH, and you remain with this O. So what does that imply? You're going to increase the hydrophilic nature on one end, which is the head, which is the phosphate head, and then the tails, since they are just the long chains of hydrocarbons, they become hydrophobic. Okay? They become hydrophobic. And this property, so if you end up forming your phospholipid with a head which is hydrophilic and tails that are hydrophobic, this property here is so important as far as formation of cell membrane is concerned. Okay? It is so important as far as formation of a cell membrane is concerned. Okay? So, the two ends of the phospholipid, they show different behaviors towards water, whereby this hydrocarbon tail is hydrophobic and therefore excluded from water. However, the phosphate group, this phosphate head, okay, is hydrophilic in nature, and so it has too much love for water. Okay? Now, how is this an important factor in nature? When you have your phospholipids, many of them, okay, and you put these phospholipids, okay, in water, many of them, the phospholipids, and they are put in water, okay, the phosphate head that are water loving, they will assemble themselves, okay, towards water, okay, they will assemble themselves towards the water, okay, okay, and the phosphate tails that are hydrophobic, they will arrange or they will assemble themselves away from the water. Okay, you can, which we call it hydrophobic interaction. So the heads, they will arrange themselves in the same orientation, and the tails also will arrange themselves in the same orientation. As a result, you end up creating something like a membrane that will surround these cells. That's why when you have to study your cell, and this is your cell membrane, and you know that the cell membrane, it's a double layered structure of phospholipids, where you have one phospholipids pointing inwards, or one layer of phospholipids pointing inwards, and another layer of phospholipids, okay, the head is pointing outwards. That's how it is arranged. Think about why this arrangement. Why that arrangement? It's because the extracellular matrix, here, it is filled with water, and also the intracellular matrix, the cytoplasm, is also filled with water. So as a result, the heads will arrange themselves outwards and inwards, hence projecting their tails inside, where we do not have water. And as a result, you come up with a plasma membrane. Okay? Yes. Any questions for me as far as this is concerned? So basically that's how simple it is. So let's talk about the steroids, and this is also some simple work. Steroids are a class of lipids. Okay? They are a class of lipids that are characterized by the carbon skeleton made up of 4 fused rings. And what are the 4 fused rings? It's this one. You have this as your first ring, and then this as the second ring, as the third, and the fourth. They are 4 fused rings. Now, all steroids, all of them, okay? All steroids, they have this basic structure. However, now they are different basing on the groups that are attached. Okay? The groups that are attached on these rings. Okay? So basing on the groups that you have, it will determine which steroid are you, whether you are going to be a hormone, and if you are to be a hormone, which hormone are you going to be? Is it progesterone? Is it testosterone? Or it is estrogen? Okay? Or is it cholesterol? Because cholesterol is also a steroid. So is it cholesterol? Because it is also a steroid. And which group is going to be attached? For example, you can have a look. Progesterone, same, okay? Same rings, but the difference is now on the groups, whereby you can see here you have O, and testosterone you also have O, and here you have CH3, and here you have CH3. You have the CH3 here, and you have the CH3, but now the difference is on this carbon atom, okay? Whereby in progesterone you have the CH3 and then O. In other words, it's a ketone. But for this, okay, you have the OH. And that so-called minor difference, it is enough to make these hormones different. Whereby this is found in males, and this one is found where? In the females. And this one is responsible for the male's secondary sex characteristics. And this one is responsible for the female's sex. Not sex, but maintaining the uterus, okay, from being shed off. It is this one which is responsible for maintaining the secondary sex characteristics. So basically they are the same, okay? Basically they are the same. So I was teaching, and then somebody asked that what is the disadvantage of synthetic steroids to our bodies. Synthetic steroids to our bodies. Now the synthetic steroids, if you take too much, maybe even before you take these synthetic steroids, they are steroids, okay, that are not naturally made in our bodies, but rather manufactured in industries. Synthetic, okay, they are manufactured where? In an industry, in a lab, and then they inject it in your body. For example, these family planning hormones, family planning, they inject you with mostly progesterone so that you increase the levels of progesterone hormone in blood. And when you increase the levels of progesterone hormone in blood, then your body perceives it as if you are pregnant. That's why ladies on family planning, they miss periods frequently. Frequently. Ladies here no. That is if they have ever used one. Okay? Why? Because the body perceives as if you are pregnant. So now overuse of these synthetic steroids, it is also not good. Okay? Why? Because these are steroids. If they accumulate in the body must eliminate them. Okay? By converting them into cholesterol. Now the effects of cholesterol so much that one of them, it forms LD, high density lipoprotein molecules, LDL. And with this LDL, then it increases the risk of high blood pressure, that's hypertension, obesity, and stuffs like that. Okay? So if you take excess, if you take too much than what is required, then those are the ladies you hear complaining that me I started family planning and now I'm obese. That me I don't like family planning, but that whenever I take it, I become too fat, too fat. So probably disrupt with the body's physiology. Okay? And it's not good. And then other risks associated with it. So these are our steroids, okay? And the steroid hormones. Maybe if there is a question, then we can proceed. Okay? Then for waxes, these ones, they are just formed by combining our fatty acids, the usual fatty acids, with alcohol, with any other alcohol other than a glycerol. Okay? And they're extremely long, saturated hydrocarbons, and since they are made up of a high hydrocarbon chain, then they are impermeable to water movement, and so they are waterproofing materials in both plants and animals. Okay? And then there are storage compounds in some seeds, e.g., the castor oil. Now, castor oil, how do you call castor oil? In mother tongue, how do you? Mm-hmm.